congratulations to all speakers for being selected and voted. It's a huge honor. And secondly, huge thanks to participants for voting for us and bringing us there. We are only here thanks to you, and thank you very much. So today, this is a talk on the SCADA security. And yeah, I already have a few questions today from the participants, and they say like, well, SCADA is still a mystery for me. So today, hopefully after today's talk, you will understand more about what it is to hack like SCADA systems. Okay. So what are the industrial control systems? So that we align on the vocabulary. Industrial control systems, also known as SCADA, is a bunch of computers which are hooked up together to automate the process over the automate the control over the physical process, which could be like power generation, water treatment, manufacturing facilities, and the like. So this is how this IT system would look like in the architectural view. And the data, which is the entire IT architecture, is there only to process the data which comes from the physical process. So in the earlier days, we didn't have IT systems, we just have mechanical systems. So IT system is not something what you really need to run the process, but this is how we make the processes being more efficient and more economically efficiently. So this is, at the upper level, we will have something what we call business domain. This is where they plan how much we can produce like in a year or months. And because of this, this engineering systems consists of the computational elements, networks, and the physical processes, also called cyber-physical systems. And in contrast to the traditional IT systems, the interest of the attacker is in the physical world. The attacker wants to bring our process in a specific state or to make the system perform specific actions. So I think the James Bond movie is something what like reflects the best how the progress is developing like across the years. And like in the Casino Royale, we still had these nice beach scenes and everything. In the next movie, there was already like nothing like that. And finally, in Skyfall, we've got a hacker, which is of course like I think a little bit pity. And if you remember in the Skyfall, there was a villain, Silva, his surname was Silva, and he was sitting in this cell prison, and then they connected his laptop to MI6 network, and then the system got hacked, and with that malware, the villain was able to escape the prison. And in fact, that was a cyber-physical hack. The attack was launched in the cyber domain, but the hack was about causing specific event in the physical world to unlock the door. What is this in cyber control system security? And one of what we hear mostly about that there are so many vulnerabilities in that. Well, that's not an old news. Like in Windows and the traditional IT systems, there are a lot of vulnerabilities. In fact, there are so many that we are not interested in talking about them anymore. But here's a kind of new domain. We're still all excited, and the vulnerabilities are reported in the packs of 20 and 50 per day. So there is still like a lot of excitement about that. So the more interesting is that like, okay, so what exactly does it mean? What the attacker can do to the system with those vulnerabilities? And this is where it's become interesting. So if you look into the advisory, so most of those vulnerabilities after responsible disclosure, they go into the ICS cert advisories, which tells you, okay, how severe is the vulnerability and what is the potential impact. And in fact, the suggestion is typically, well, impact you have to evaluate yourself. We don't know. Depends on your system, depends on the criticality. And this is just like, okay, so how exactly the operator is supposed to evaluate that specific impact of the specific vulnerability? So the typical understanding about the post-exploitation SCADA is that you just hack in one of those devices and there will be some specific button which you press and the system will fail exactly in the way you need it. The truth is that button does not exist. And actually the hacker has to create that button. So if you think about any hack in the IT domain, it's not about exploiting the vulnerabilities, it's how you can actually design an attack and make it useful to your goals. So for example, let's look again, and this is the previous advisory which I showed was about vulnerability in the industrial switches. So this would be like a typical configuration about that. So what exactly the attacker can do to the process if he has access, full access on this industrial switch. So here's your target plant. What will you do to it? How exactly will you blow up this place? And the fact is that you really need to know something about the target plant and how those system works. So just to show an example, so this is 4 sensor signals which represent the pressure in the reactor. Reactor in the chemical plant typically is the heart and one of the value targets. Because if you blow up the reactor, it's a lot of damage, and secondly, you just like have to stop the production. So, and this is, for example, if you will launch an attack on that switch at some random time, trying to actually, with a goal in mind, to raise the pressure. And the truth is, if you will just do it blatantly without, like at random time, without understanding anything, you can actually, the impact of your attack can range from like nothing to in economic and efficiency. Here we have a near miss, but because the attack was only 8 hours long, we here missed the safety point. And in this case, we actually reached the safety limit, and actually the plant went into the safe shutdown. So it is not really that you can jump into the plant and do anything you want. So understanding the impact of the vulnerability really needs you need to know how exactly the attacker can exploit that vulnerability, what kind of attacks on the control system, on the process the attacker can launch, whether any further necessary conditions are required, and how severe is the potential impact, because the vulnerabilities in a certain part of the plants are actually not critical to the plant. So if a specific piece of equipment is controlling something what is really not important, like critical to the performance of the plant, then you don't really care about that vulnerability. So basically answering all of these questions requires understanding how the attacker interacts with the process, with the control system and with the process. And at the Hack in the Box in Amsterdam, we actually thank you, by the way, for selecting that talk as well. We actually were demonstrating how difficult it is actually to launch an attack from the switch, and how much knowledge the attacker needs to acquire to launch the attack from the switch. So in order to understand how do we design attacks on the SCADA system, we actually need to understand how process control works. And I will, in the next 10 to 15 minutes, I will tell you everything what you need to know in order to understand any cyber physical or SCADA hack. So what is the process control? The easiest way to understand process control is from the example of the heating system, or maybe if you're here in Asia for the air conditioning system. So you want, let's assume you want to keep a specific temperature in the room. So you can always, let's stay with the heating system. So you can always, of course, manually adjust the valve into the furnace system, controlling the amount of fuel coming into the furnace. But this is not sustainable because you have to do it manually all the time. And in 21st century, we automate everything. So for that reason, we now have all thermostats. And it's all start that you have to select you need to select a set point, or basically the desired temperature. Then the thermostat will constantly measure the temperature in the room and will automatically adjust the fuel or amount of heat coming into our into our heating system. So this all happens in a control loop. So all control over cyber-physical systems, whether it is cars or robotic hands or any continuous processes or manufacturing, is happening actually in the control loops. So we have our furnace. We have sensors which measure the temperature in the room, in the ambient temperature. The temperature goes into the control system, which computes the difference between the desired temperature and between current temperature, and compute the command to the actuator, which goes then into the furnace. So in a traditional, like large plant, there will be a lot of control loops. For example, one of them is here. And one of the difficult things about them that they all interact. So for example, if I will adjust valve in some part of the plant, everything else changes because those control loops, they actually interact and they actually interrelated. So in a large-scale operation, like in this case, we have a water treatment facility. The control logic becomes a little bit more complex than the thermostat. You actually need a specific control equipment to control such processes, and such equipment called programmable logic controllers or PLCs. So this is a photo from the actually test bed, which is actually located here in the Singapore. It is a test bed for water treatment facility. We have here sensors, and we have an actuator. In this case, it is a pump. So the cables from this equipment is going into the wiring cabinet, and eventually this is the wires, and eventually it all comes into the PLC. So the PLC controls the processes in the same way in the control loop. So it takes the measurements from the sensors, copies them into the input buffers, execute control logic, compute the control commands to the actuators, and so on. So what is the control logic? Control logic, it's a program in the PLC which defines the logical sequence, what should or what should not happen to the process under which conditions, at what time, and in which order. It's programmed in graphical way most of the time, so it's not like Python or Java or something like that. And the thinking in the control logic, the programming thinking is like binary. If this and this, then do that. If not this but that, do that. So something like if the tank pressure, if the pressure in the tank like higher than 1,800 kilopascals, reduce the inflow in PLC3. So control logic does not compute the control commands to the actuators. Yes. So what is also important, what important information you will find in the PLCs is interlocks. So we used to have a lot of mechanical protections in the system, like cage-in basins, a lot of redundancies, mechanical protections like relief valves and so on, manual valves. But it's very expensive to maintain the physical protection. Therefore, they now like gradually all goes into the software. So now we all of like things which should not happen to our process, they are also in the software right now. And this is of course very interesting to the attacker. And if the attacker is not able to overcome those limitations, like for example in this case, the motor should not be running if the valve is closed, because in that case the system should stop. And if the attacker has this brilliant idea to burn the motor while closing the supply of oil, he will not be successful because the control system will not allow him to do so. It will just like the system will go into stop. So yes, so that is what that the control logic does not have influence on the shape of the signals, because this is determined by the control algorithm. And the most common control algorithm on the planet Earth is PID, which stands for proportional, integral, and derivative. So basically the control command here is computed based on the three components, which is represented by the differential equation. So if you see here, there is our set point, there is a process state variable, and then we compute the error, and from here to here we come over this equation. So approximately at this point, this is where all IT people say, well, I don't want to exploit SCADA. It's just like ugly, I'm not interested. But there is no way you can skip it. So understanding like this algorithm, and especially this is tuning parameters, so this is coefficient, this is tuning parameters of the control loop. This is what actually defines the behavior, physical behavior of the process. And finding the right tuning parameters is so difficult that the guys who are actually capable of doing it very well, those are external consultants which earn like tons of money. And doing it right will actually what define like whether output will be noisy or not, and so on. If you thought that was ugly, it can get even worse. So one of the important things, so physical processes are actually dynamic systems. So the state of the process changes over time, all the time. So it's not a static system. And the attacker, important to understand how the system responds to those control commands. And interesting thing about physical processes that, for example, if you adjust the control commands of, let's say, a valve, if you adjust some actuator, the system does not react immediately. There will be always so-called dead time when system does not react, and only after that it starts to change. And then once the system reaches the 63% of the desired output, this is time which is called the time constant. And all of this information is extremely, extremely important to the attacker because he has to actually synchronize actions. And actually also this timing parameters is actually what represents vulnerabilities in the physical processes. So now I wanted to give you an example. What is that physical vulnerability? So you have here the Tennessee Eastman process. We have here a reactor. And the pressure in the reactor is actually controlled by the purge valve. And 15 is actually just this size, the throughput of the valve. And it's relatively small throughput, therefore the time constant is actually 60 minutes, which is a long time. So basically, if you want to bring the pressure in the reactor from here to here, it will take you like more than actually 1 hour. It's a slow process. So now we have here the input, this is the input flows of the chemicals which runs into the reactor, and you can see this is a large flows in comparison to the output of the purge valve. So this is exactly this situation is what presents a vulnerability in this plant, and actually this place would be called the bottleneck. So this is what the attacker can exploit. So if the attacker would be able to raise the pressure in the reactor faster, then this valve can release the pressure, then he actually can the reactor to burst. So now the attacker needs to figure out how exactly he can raise the pressure in the reactor. So for example, the attacker can stop the mixer. Then there will be, for example, some hot spots in the reactor. The attacker can actually modify the inflow ratio of the chemicals, changing the kinetics of the chemical reaction, maybe making it happen faster. Or the attacker, for example, can stop the cooling system. And for example, if the attacker will not be able to, for example, if the system, if this chemical reaction is not very, let's say it's not very hot, then probably the rise of the pressure will not happen too fast, and maybe the attacker will not succeed. So it's always a combination of you need to find the vulnerabilities in the physical and control design in order to actually do something to the system. So SCADA hacking is not about just hacking into the device. It goes many steps further, and this is what this talk about. So the PLC cannot control the processes on its own. The problem is that the PLCs, they don't have the process, they do not see the state of the entire plant, and also the PLCs do not have the time trend. So that's why we have human human operators which watch the plant around the clock. When we say that the operators watch the process, it actually means that they respond to alarm. Things go wrong in the plant all the time, and there are a lot of alarms flashing on the operator screen. So there would be probably 10,000 sensors, and the operator will be watching just several of them, and the rest will not watch. So if you're an attacker and you understand how human operator sticks, you actually can, and if your attack does not rise in alarms, then you may be sure that the operator is not actually watching and will not take compensating actions. So many people believe is that like, oh well, you know, like we don't need actually to hack all the time, all the way to the sensors and the PLCs. If we get access to the HMI, we actually we already can do anything we want to the process. And the truth is, it's we cannot, because it is expected the operator will do wrong actions. And there are a lot of sanity checks, those interlock in the system. So this is, for example, HMI of the ice rink control system. So, and there is no such button like unfreeze. There are a lot of pumps which pump the cold and hot water. And even if you will try to stop any of this pump, in most cases you will not succeed, because the system will tell you, well, you cannot stop this pump before you stop that pump and before something else happens. So even trying to press something randomly in the system may not necessarily allow you to actually do something to the system. So, and Also, one of the problems with this, with having access just to the HMI, is that the time constant, the definition of the real time, is actually goes in this direction. So certain actions has to be synchronized in the matter of like seconds, and this is what you cannot achieve from the HMI, because at the HMI the timing is already like in the tact of minutes. Okay, so now you know absolutely everything about how to, like, all necessary information about cyber-physical system in order to understand any hack. So the interesting question is also, why should you hack SCADA system? And this what is also related to the talks which we've heard today in the morning, that the attackers actually are cyber criminals. And it's all about like making money, and industry means lots of money, so that should be like very attractive area for them. And unfortunately, most of the information about the accident on SCADA systems are classified, and also the process owners, they do not report such cases because it is bad for their reputation. And secondly, even if you will report that you've been, for example, extorted, might be the case that actually the government will be running after you, like seeing like whether you maybe have some compliance or safety issues. So you prefer not to report. But we have some certain bits and pieces of the information on the internet. And we also have the rising, if you will, like, it's really absolutely amazing how the situation about SCADA hacking has changed within even like last 6 months. We now have SCADA access for sale on the forums. We now have, like, okay, 0 days for SCADA was in sale for more than 3 years, but now we have access to the SCADAs, and now we even have specific SCADA hackers for hiring, and there is a demand on that. So there is really a lot of interest towards SCADA, and when we talk about that, well, okay, let's kind of do something to our system. You always, when we think about designing this SCADA, like cyber-physical payload, as I already explained, you actually need to put certain commands to the system which bring, which allow you to control system in a way you need it. And when deciding on which commands you want to put into your payload, you actually need to understand what is your attack objective. And that starts from everything like, what is your actual intentions? Why do you hack SCADA? And so in general, there are like all the, like what you can do to the process, you can be roughly divided into 3 groups. So first of all, you can damage the equipment. You can either overstress the equipment, like this is what has happened in SCADA, and with that you will shorten its life cycle. Or you can actually like intentionally violate safety limits and make the equipment breaking. The second group of the attack is production damage. For example, you can reduce you can mess up with the product quality. You can reduce product quality, for example, its purity, or you can actually reduce the production rate. The second approach is to increase the operating cost. For example, to increase the energy usage or to increase the loss of the raw materials in the purge. So obviously, if your production becoming more expensive, you're becoming less competitive in the market. And the third approach would be, for example, to increase the maintenance cost. For example, make the plant operators troubleshoot the process, maybe even hire expensive consultants and so on. These first 2 groups of attacks, this is what they are exactly, those types of attack will never make the headlines. So this is something that will not be reported, and the companies will never say that they have these problems. If you would really want to damage the reputation of the company, then you wanted to make it non-compliant. So most of the manufacturing, control, let's say industrial control system or actually production systems, they're heavily regulated, and all of those regulations are easily available to the hacker. So it's easy for you to come up with a design. So the most damaging attack would be an attack on the safety, and here I refer to the occupational and environmental safety. So for example, occupation, it's like hurting the humans, and environmental is like, for example, heavy oil spills. The less damaging attack would be on pollution. This is, for example, water or soil contamination. And the third group of attack could be violation of the contractual agreement. So most of the production, you have to deliver on time, and even being delayed even by a day costs a lot of money, and also reputation. So when the attacker is rational. The attacker would think okay, well, so what type of attack would I want to launch on the facility in order to achieve, let's say, to achieve my goals? And this is how the attacker would start thinking about that. So equipment damage is something what comes into everybody's mind first. But the problem is that this attack is also reversible. So if you want to do it for extortion, to demand money, the problem is you can't undo the breakage after that. It's also the collateral damage is unclear. So for example, if you break the reactor, it will burst, it may contaminate, cause heavy pollution problems, it can kill humans. So therefore, the breakage attack can easily transform into the compliance violation. The problems with the compliance violation is that it must be reported to the authorities. This may be what exactly you want to damage the reputation of the company, but the problem is that after it will be reported to the agencies, there are very skilled guys who will run after you. And if you are not so sure that they will not able to find you, you don't want those guys run after you. So this is probably, serious argument whether you want to launch this type of attacks. The good thing, as I mentioned already, the compliance regulations are easily available, so it's easy to design such attack. But again, the collateral damage is unclear, and if you will cause more damage than you actually wanted, then again, very serious guys will very seriously run after you. So out of these considerations, it's actually attack on the production damage is something what is really on the safe side. It must not be reported, and the company will probably also not complain much about that, to the authorities. So, and it can be also easily masked as just inefficiency in the plant. So that sounds like a good scenario. So this was exactly the case. This is what type of attack which I selected to hack. So this talk is about what do we need to do? It's how do we design an attack on a large facility such as a chemical plant from the beginning, entering the system till the very end. Because what we know so far about the SCADA payload, that the attack somehow happens. We don't know how, but it's just there. So I want to break the mystery. So who would like to launch such type of attack? So one of the cases, it could be a good, strong argument for the extortion attack. And secondly, it is, for example, if you want to kick out the competitors out of the market, or if you maybe want to buy some certain supply of the chemicals and then make this company less competitive and sell your chemicals a little bit, overbid those guys on the stock exchange for goods. Also, we talk a lot about in many cases, it's state-sponsored attacks, and the cyber criminals are differentiated, it's two different group of criminals. Well, state-sponsored attacks are also cyber criminals, and actually they often support the national businesses in order to beat the competition overseas. So that is really attractive attack scenario in a lot of scenarios. So now we are ready to start. One of the problems of hacking SCADA and why we do not have a lot of research and practical work done on it is that in order to design some payload and actually develop your skill on hacking physical processes, you need experimental test bed. So of course you can buy a chemical plant, and the problem that of course they're very expensive, that you need a whole army of people who will run it for you. And then if as a result of attack you will break your plant, you will need a lot of new money to fix it. So actually, let's say, developing your skills on the live plant is not sustainable. And therefore, actually, in reality, the research on the control engineering, on process engineering, chemical engineering, happens on the plant models. So I picked the publicly available model of the chemical plant, which is vinyl acetate. It's a realistic plant with a realistic behavior. So vinyl acetate is a commodity chemical which is used as a building block for manufacturing paints, resins, plastic, and so on. So it's a very popular type of plants. So we will now go through the stages of cyber-physical attack. We want to cause persistent economic damage on the plant. And what I did not mention on the previous slide is that persistence is a keyword in what we want to achieve. Basically, we want to avoid the attribution of the plant misbehavior to a cyber event. And then you need some strategies to do so. So the hacking of the plant has actually happened in specific stages. And I picked the stages, so they were first presented by Jason Larson in actually 2007, but they never been ever like used by anybody else before. So what we've done also, we did really formalize those stages, and we specifically described in the paper which tasks the attacker needs to do at each stage. The perfect knowledge at each stage is never achieved, and actually the attacker will need to circle back to certain stages and maybe even perform the exercise on the same stage again and again. So we will now go sequentially through all the stages. So the first is access. You need to get access to the plant. So in the earlier days, how you would go about that. So you will find some 0-day on some user computer in the office domain. Then you will use any ingress connection like antivirus updates, database links, backup system, and you will get in the control system. Once you're in the control system, you're good. There is no security there, so move freely. The challenge is here that most of the equipment will be specific control equipment, which is not a Windows machine. So if you don't have skills in hacking those systems, just no problem, just grab a specific exploit pack. So this pack, it actually comes from Russia. It contains all available exploits for all available vulnerabilities which were reported today. But the point is also that several companies already have got this right, and sometimes it can be a little bit challenges to get in like through this. And actually in the modern days, how we would go, the modern hackers, how would they go? Because of many of that equipment is now connected to the internet, just go into the ICS sort database, pick up a vulnerability of your choice, which is remotely exploitable, then scan the internet to locate the vulnerable devices and exploit. So this is one of the beautiful works was done by Erin Leverett when they were scanning for the Codesys devices. And Codesys is a runtime system which runs on the PLC, and that would allow you immediately full access to the PLC. You can then reverse engineer the logic and so on. Also, what the attackers are doing right now, so this is already like sort of a little bit SCADA specific hacks. So for example, Bit9 is actually a solution for whitelisting of the applications, and SCADA is heavily using it. So basically they stole the sign-in certificate and they signed the malware, so it was actually whitelisted. Then the Telvent is a leading software supplier for the power grids. So the attackers has hacked into the servers of Telvent, and they really changed the code on the software. And like one of the most popular now ways to get in is just the hackers actually infect the SCADA installers on the SCADA installers or patches on the web pages of the software suppliers. So basically this stage is the stage which is very well understood to the IT hackers, but this is also the stage which is last, which is known and understood to the IT hackers. Starting from after you got access, you need to start thinking as a process engineer, as a control engineer, chemical engineer, mechanical engineer, and so on. So, and first is that you need to understand actually what is this plant, how it is built, and so on. So everything what we've been like learning in this in the section on the process control basics. I used to have here this joke about the stripper because like that was my first actually, how to say, experience with the control system. I was reading the specification of a plant and there was a word stripper, and of course like what the stripper means in the chemical plants, I Googled it and you can imagine what I found. So you really need to understand the equipment. And so this is the type of information which the attacker will be after the attacker gets access. This is what the attacker, how the attacker will proceed. So first and foremost, you need to understand what and how the process is producing. Even if you know that it is a vinyl acetate plant, the exact chemical reaction and the kinetics is unique to each plant. And actually, it is not even known to the plant owners because it's typically, it's intellectual property. It belongs to some like subsidiaries. So you would actually need to go and perform espionage on the third parties. Then you need to know how the plant is controlled, how it is built and wired. If you've seen, those plants are typically like a couple kilometers long and you need a bicycle to move along. And also, of course, you need to know the operating and safety constraints because this is exactly what is the most important information for the attacker. So this stage is already very well understood by the attackers, and this espionage against their, let's say, industrial facilities and like power and everything has been happening already for a long time. Every week we discover some espionage campaign, and the instances of the malware, of some malware, are already dated to 2003. So the attackers are interested in such documentation like chemical formulas, piping instrumentation diagrams. This is list of equipment, field equipment list. This is the wiring diagram and so on. So after the attacker will gather the first initial understanding of how plant works, he can actually start thinking, come up with the first design like, okay, how I'm going to cause economic damage to the plant. So the easiest way is to actually disrupt the pipe which carries the final product. The problem with this attack, it is easily noticeable, it's easily repairable. So this is not sustainable. It will not give a sustainable effect. The rest of the plant can be roughly divided into two groups, refinement and reaction. Refinement is the largest part of the section. This is exactly which is 2 kilometers long. So the attacker will have a lot of opportunities to launch his attack, but also the operator will have a lot of opportunities to notice the attack. And even if your product will not be refined properly, you can always collect it and refine again. So, well, maybe it's kind of, let's say, it's unclear whether it hurt that much. In contrast, if you will disrupt the reaction in the reactor and make it, for example, make reactor producing less product, let's say make it less efficient, then basically then the entire refinement section is already meaningless. So this is really sounds like, like a good attack scenario. So therefore, in this work, we now concentrate only on the reactor section. So then the attacker, so for example, now we know like approximately the part of the plant which is interesting to us. We need to start discovering the control structure of the plant, like all the control loops. And we need to figure out what is the configuration of the control loop. Thanks God, now the attackers have easy times because there are a lot of applications, smart applications, which will actually contain this information for the attacker. It used to be some paper spreadsheet. Now you have everything in one place. So this is, for example, asset management system from Aveva Systems. Never have heard. Available on the internet. So, for example, we now see that is a pressure transmitter. The control loop service, it is actually reactor. We have the serial number. We have here tag. It's basically how the name is how this variable is stored in the PLC. We have here actually process conditions, how this sensor is working in the process. We have here information on the calibration of the sensor. And what is more important, we actually have here the surname of the guy who is allowed to actually calibrate this instrument. And this brings us back to the keynote speech today in the morning, so that if you now have the surname of the guys, you first know which actually credentials you need to obtain if you want to miscalibrate the sensor. And secondly, you also know, like, for example, which guy to bribe. And you can easily find him on LinkedIn and so on. That's a lot of important information. So one of the hardest part at this stage of the hacking processes is reconstructing actually, for example, the first what the attacker will probably find about the plant is piping and instrumentation diagram, but he has no idea how that will eventually translate into the actual equipment in the field. You need to find the right PLC, which is, you need to find this variable in the control logic code. And this is the translation also how this device is called here, how it is variable here, it's not the same. And there are a lot of translation stages. So it's extremely time consuming. However, what we've seen the Havoc malware. So the attackers are already here at this stage of cyber physical hacking. So one of the way to the query the field devices and the text is actually to hack the OPC server. So every of these field devices, like sensors and the actuators, they speak proprietary protocols. And they cannot speak to all of those IT systems on the upper layers. So we have here OPC, which actually allows them to understand each other. So the Havoc was actually querying, was searching for the OPCs, tried to fingerprint them, and also was looking for servers and users. In the versions of the Havoc which was found online, the malware did not actually specifically was querying process data, but the only reason why the attacker would want to be here and understand all of that is to actually further query the data about the process. So we probably here there are two conclusions: either that is the next stage, and we will see that malware later, or the attacker is already, we just did not catch this type of this malware yet, this version of malware. So with that, so basically we now will have to find all the available controls in the reactor section, which will actually allow us to do something to the process. Since I was working in the plant, and this is how, with the models, this is somehow they call them this strange way. So this is just the numbers of the available controls or valves. The problem is that if you think that after you locate the controls, you're done, it's wrong. The problem is that your wish is my command does not work for chemical processes. They will, if you will push process into some undesired state, it will actually, it will start behaving in a strange way. And if any of you has kids, then you know that we all know how to raise perfect kids, but they never behave in the way we expect them to behave. So with that, we actually transit into the control stage. So the discovery stage was all about understanding static behavior of the process. And the control stage is now we start trying to understand the dynamic behavior of the process. So the problem is that once you hook up equipment together, it starts to being connected to each other over the physics of the process. And this is where the IT guys get it often wrong. They think that after the security boundaries is actually something in the IT world. It's not. Even if two equipment, like pieces of equipment, do not talk to each other electronically, they do talk to each other over the physics of the process. Physics is actually communication medium. So if you adjust, for example, temperature, the pressure will change. All of those effects will propagate downstream and may here cause a condensation in the condenser and so on. So the attacker needs to understand how much and what he can change in order to achieve certain process behavior, and also before he can raise the alarms and make everything switching off. So this was the example which I've shown you before. So this is I adjust here valve, everything else changes. And the funny thing that, for example, here this is actually this is a flow and this is the temperature. And you can see that basically the curve of this process change is actually pretty much the same, but the spikes are somehow opposite. And you would say, like, what the hell? The problem is that there are, if this is a control loop just a little bit expanded, there are millions of parameters which actually influence on the shape and the size of those spikes. And for example, in the talk which we're presenting in Hack in the Box in the Amsterdam, we've been talking exactly about these issues. And in those exploits which we presented there, we have to take a lot of those parameters into account. And accounting for those parameters, we actually need to put it into the final payload. So for example, I've been talking before on this controller tuning parameters. So, and for example, one of the problems which we've been having in, this is refers to this point, that you might not necessarily be able to control obtained control. And one of the problems which we have been facing is control loop ringing. So because of the bad tuning of the controller, this was, the response of the process was having this shape. And you would say, like, why do I even need to care? Because it's actually, the spike is so tiny, like, it doesn't matter. The problem is that this effect propagates downstream, and in the other control loop, it caused already spikes of ratio 1 to 150. And then all of those spikes were actually immediately hitting alarms, and this is what we did not want to have. So in fact, this was one of those control loops which we were not able to control. So another problem why it is difficult to control physical processes is that they are nonlinear. So what does it mean? It means that the output of the system is not proportional to the input of the system. So, for example, think of boiling water. So the way how the water behaves when you heat it from like 70 to 80 degrees is completely different how it behaves when you further heat it from 80 to 90. And the behavior of the physical processes to us, to human, is only known to the extent of its modeling. We model every physical phenomena. And those models are then loaded into the controllers and using the controllers to control the processes. So if the process was never expected to be operated at 90 degrees, it means that this control model is not available in the controller, and the controller will control the process in a very strange way. So, for example, if you look here, you see it's clearly that this response to some command of the controller is nonlinear. And again, all of those ugly spikes, this is what triggers alarm, and this is what we don't want. So in fact, so basically those were some certain challenges which we were facing at this stage. And then basically we tested the response of the process to two types of attacks. One of them is step attack, when you bring the process into some state and leave it there. And another was periodic attack. So basically you attack the process, let it recover, attack it again, let it recover, and so on. So how you will execute these attacks, it's already a large topic on its own. And I have like a paper, like 20 pages, where you just discuss like challenges of launching even these two attacks. So this was like basically we tested all the control loops to many different parameters of the attacks, and this is the idea is that you have to actually get the mental model of the dynamic behavior of the process. So this is what we kind of tried to put it into some spreadsheet, Excel spreadsheet, and obviously just because it was kind of first exercise of this type, obviously that was not a, let's say, best approach possible. So what we are trying to do it, I will tell in the next couple of slides. So the outcome of the control stage is that you try to kind of categorize the available control loops according to their usefulness. So you don't want to use risky control loops for your final attack design. And then also what we also have done, we've performed like we found the parameters of the attack parameters which do not cause alarms. So we know that, okay, we can move the process this far before we raise any alarm. So yes, and what we are trying to do right now is basically, it's a strange way to, we're trying to actually find the automated way to extract dynamic models of the dynamic behavior of the plants. So what we are doing, that was actually, I picked this idea from the Jason Larson, who was representing sensor signals in, extrapolating sensor signals in forms of line segments for sensor correlations. But the idea was also later that we actually can, maybe I'm now supervising this master thesis, that maybe we will be actually able to represent the process behavior in create some fingerprint, like if I change here, so how the rest is changing. So, and I can clearly see that if, such information will be valuable assets to trade on the black market. So like basically you can trade the fingerprints of the processes. So now when we understand which controls are actually available to us, only now we can start designing our damaging attacks. And this is one of the stages which is the most difficult for the IT guys, because you typically need really the input of experts. So you need to understand how the equipment fails, or how, when I started, I really have to go a lot around to consult a lot of process engineers. I now kind of a little bit more experience. I already have own ideas. And actually, if you will start reading the accident report, there are a lot of YouTube videos. And actually, just take any book on optimizing processes, and because this is the way how you can de-optimize them as well. So why damage stage? I want to reemphasize why damage stage comes before the control. So at CCC, I presented this beautiful attack scenario, which is absolutely awesome and was quoted several times. So let's poison the catalyst in the reactor. If you poison the catalyst, this is the most expensive and damaging attack to the production. It was awesome, awesome, awesome. The problem is that in order to kill the catalyst, you need to raise the temperature in the reactor to above 200 degrees. And you need to keep the temperature for a certain time in order to catalyst really to die. And the problem was exactly that I was not able to control that valve which allowed me to raise this temperature. So I was not able to raise the temperature for long enough to really cause damage to the catalyst, because because of all of the interdependencies, there was alarms, and even if I was suppressing alarms, the changes were propagated further, and eventually the system was going into the safe shutdown. So therefore, it's really, you need to know first what you can control and then start with the damage design stage. So one of the problems is that the plant is actually not designed in a hacker-friendly way. So in order to actually measure the impact of your attack, you need to be able to have specific sensors. And the fact that there might not be sensors at the required locations, or the information about the process is spread across several sensors, and the attacker need to figure out this information, actually invade more devices. So what was our problem is that we wanted to make reactor producing less product. For that, we need to measure the concentration of the molecules of the vinyl acetate in the reactor exit. The concentration of chemicals is measured by the analyzers. There are 4 of them in the plant, but none of them in the reactor exit. The reason for that analyzers are utterly expensive, and they are only installed in the location when really absolutely necessary. So actually also to compute, it's not sufficient just to measure the concentration. You need also to flow measurement in order to actually compute the amount of chemical. And the only place where this combination is available in the plant is actually plant exit. The problem is that if the attacker changes something here, this measurement will be available approximately after 8 hours, which is obviously too late, and it's not sustainable to work in that way. So we really, really need to find the way to measure the impact of the attack in the reactor exit. And here's the thing. There are 2 types of measurements in process control. One is the technician answer is just like, well, something is decreasing. An engineering answer, which says it's decreasing by this much, by this time, or at this velocity or this speed. So, and actually certain sensors, because many measurements in the plant, they're actually correlated. So you can use correlated measurements as a proxy sensor to actually derive state of the other sensor. And for us, it was temperature sensor in the reactor exit. So if less reaction is happening in the reactor, it means that the temperature in the reactor exit will decrease. So if you will, so with actually reactor temperature, you can see the impact of the attack, whether our attack is successful or not. The problem is that it only tells us if the reaction decreasing, but it does not really allow us to accurately compare the performance of different attacks. And it was absolutely a large problem to us. So for a couple of weeks, we were so stuck, it seems to us, I wanted to give up because I thought that I cannot do this. And since I already have a failure with the catalyst, I really wanted to stop with hacking like altogether and never return to it. Then after some time, I remembered that actually in the controllers, there are a lot of controllers compute a lot of intermediate values in order to compute the correct control command. Also, there are a lot of optimization applications on the upper layers, which actually also try you to like help you to compute the effective control command. So I was thinking like maybe there are some intermediate computations in the controller code which could be useful to me. So after some time, I was actually able to locate the correct part of the code. The problem, and we actually extracted the numbers. The problem was that those numbers you see, they do not sum up to 100 or to 1. And if you even multiply it with flows, the numbers were actually meaningless, absolutely meaningless. But that's why we are hackers, because we never give up. And actually, after a couple of weeks, we were able finally to make use out of those data, and we were able to compute the amount of vanilla acetate produced in the reactor. And with that, finally, we were able actually to quantify our attack in dollars. So at the end of the damage stage, we actually classified the control loops according to their damage potential. So you basically then, for example, this does not cause too much damage, so maybe it's not useful, and so on. So you basically then, in your final payload, you will put a couple of attacks on those control loops. One of the challenges, the problems and differences between cyber-physical hacking and IT hacking is that in cyber-physical hacking, you change things in the physical world. And you can't just basically hide the effect by erasing the logs. Oh, no, your equipment is not broken. It's just like... So actually, the attacker has, during the execution of the attack, he has to actually hide the attack from the operator, and also to avoid, so basically, if you will change something, they will start forensics investigations, and maybe this is this state. So you basically, what you want to do, you want to execute attack in such a way, or basically create a forensic footprint, so that they will attribute the attack to anything except a cyber event. So, for example, what you can do, you can either attribute the attack to specific events, like, for example, perform the attack only on the hot days, or dedicate the attack to specific employee shifts, so that the employee will be investigated, but not the process. So, for example, it's just like one of the algorithms. So wait until the next scheduled calibration of the sensor, perform first attack, wait until the engineer, the maintenance guys will be screamed at, and he will be sent to recalibrate the sensor, perform the next attack, and so on. The guys will drive nuts. So this is, for example, you can see here there are 4 different attacks which rise pressure, temperature in 4 different ways with different deviations. If eventually, for example, after some time, they eventually may start doubting the reactor, then they will invite the forensic investigators to actually look in, to analyze the reactor. And nobody can actually look into the reactor. So what they do, they actually compute specific metrics which describe allow them to troubleshoot the reactor. So, and if you will start changing the attack patterns according to debugging efforts of the plant personnel, you will actually avoid the attribution again. You will just, let's say, it will allow you to persist with attack a bit. And this ugly plot, actually, it's not like really very important, but we've been computing these metrics and we've been trying to find those attacks which will allow us to avoid the attribution. Another easy way to actually, it's an ugly plot, and probably you would say, oh God, I could not be interested less. But the problem is that and they will be looking for the, okay, so what started to misbehave first? And the problem is that if you will change the parameters of how the sensors are sampled and how they're filtered, actually, eventually, what the attacker can do that certain, so this is 3 this is the same sensor signal just processed differently, and eventually you can make even actually sensor signal being uncorrelated to each other. And again, they will have a problems with troubleshooting, like determining the root cause. And if they do not understand the root cause, they will not look at the right device and like where your attack is located. So this is, for example, just an example. So this is the different stages of the attacks, and there are the tasks which you need to accomplish. This is just examples at each stage, which eventually will bring you into the final payload. So you have to actually, in your final, like you have to write exploit for each of these tasks. So I'm almost done. So yes, the problem is that industrial control systems are vulnerable. They now speak TCP/IP. They are connected to the internet. But we really need to start exactly like designing, like attacking the processes more, because we need to understand what the attacker needs to do and why, because then you can look for the attacker at the right places. For now, we now have so many startups which design new solutions. Oh, network monitoring for SCADA. Whenever you ask them, like, what are you monitoring for? Well, for attack. What kind of attack? Do you know how the attack exhibits itself in a network? Do you monitor everything? You can't monitor everything, so you probably concentrate on some specific locations. So with respect to the end, if you start understanding more, like which is the challenges the attacker is having while designing the exploit, you can actually raise the cost of the attack, because security is about rising cost of the attack. So make exploitation such a way that, for example, the damage worth will exceed the attack design. And which is my last point, is that each process is unique, and it's true. Like hacking any new plant or any new process is time consuming. This was more than a year work, but there are a lot of attack instances which can be applied to many different instances. And this is our danger, because the attacker, the metasploit for SCADA is just like matter of time. And basically, this is where we need to concentrate our attention, like how we need to start to come up with the protection solutions. So with that, thank you very much for your attention. I guess I don't have time for questions, but I'm here all the time, and I am looking forward for questions after the presentation.
So we have time for one question if anyone has for Marina on stage. No? Off stage then. Thank you very much, Marina.